this topic or
Sorry.
interested in the topic, but it's something that has just got underway recently in the last couple of years for my lab, at least in my research. And so we feel really, really excited about this work on the LA River. I'd done some field trips on the LA River and, had dabbled in it a little bit here and there, but we now have funding and some interesting early findings, which I will share at the end of the presentation. I wanted to mention, since, our main audience is in Mexico, that I have been involved since the early 90s in work on transboundary aquifers, mostly along the New Mexico and West Texas Chihuahua corridor. And I had worked in a governmental agency and was, I guess you could say, the lead of the U.S. delegation, where we were tasked to put together with the Mexican collaborators and colleagues, mostly from governmental agencies, exchanges of data that were considered authenticated and verified by the US and Mexico governments. And so we had to undergo a series of pretty high level meetings at the Mexican and US sections of the International Boundary and Water Commission. Those took place from 1994 to 1998 when we published a binational report and aquifer database for the groundwater resources of the El Paso Ciudad Juarez area. And this is just the agenda of one of our meetings toward the end of our study. We had U.S. and Mexican teams working together, and this was the proposal from Mexico for preparing the binational report, which the U.S. delegation had pretty much accepted. And here we see right at the meeting some translations being done in this copy that I've retained. And this did become our binational aquifer report for the area. And as I say, it was recognized by the US and Mexico governments. It's published in English and Spanish, and it did have a database, which was the probably the most important asset provided by this whole 4-year endeavor. And that database of both US and Mexican data has been used in developing some numerical models that cover aquifers spanning the U.S.-Mexico border. And so it was pretty high level. I only wanted to mention that because it's always a pleasure to keep the collaboration going with Mexico. And so it's my privilege to talk today about work. But we're going to transition to the LA River because this is what I was told. Oh, real quickly. That binational aquifer report finished in 1998, and I came to Cal State LA in 1998, right at the very end of finishing that report when I worked for the government agency. But a few years later, I was able to develop some funding from National Science Foundation in $700,000-800,000 grant, and we did multi-year study, uh, kind of a follow-up to some of the recommendations of that database. And so here we are with in Juarez and in the Juarez Valley, collecting data from groundwater wells. And here are the Juarez Mountains, a nice anticlinal feature. There's actually a spring right here at the base of the anticline. You can't see it, but that day we were there to sample the spring in the Juarez Mountains. So yeah, it's just really a pleasure to continue collaborating with Mexico and my pleasure to present this talk today, which is switching now to the Los Angeles area because it is what I was asked to talk about. I was told that the students and faculty at the University of Chihuahua wanted to know a little bit about LA River and the water supply to LA. So, I've kind of coddled together a couple of different talks to produce what I'm going to present today, which is divided into three parts. First of all, what is the water supply sources in Southern California and specifically Los Angeles? And that's going to be a very, very quick summary because that all the details related to that could basically, take an entire semester course to cover. So that's just going to be a real quick summary. And we're going to mention a couple of issues related to some environmental regulations for total maximum daily loads of how groundwater is, ties into meeting these regulatory standards for pollutants in urban watersheds. And that comes about by catching the urban runoff and then recharging groundwater systems through small-scale operations beyond the large retention basins that have been used since the 1940s. And we'll talk a little bit about that and how that ties into some of the regulations and groundwater sustainability issues and the fact that LA is a semi-arid environment. And it does at times have some real critical water availability problems because our import water is declining due to climate change and growing population and drought and so forth. Second part of the talk, I'm going to discuss LA River conditions, some of the anticipated changes that really relate to the first part of the presentation, and then also, the fact that there's a pretty strong initiative to develop some stream restoration of the LA River. You've probably perhaps seen in some movies this massive concrete line channel. And, some people want to do a complete restoration of the entire LA River, but there's definitely some fiscal and engineering challenges to doing that. And so there are some compromise efforts that may be more realistic, at least in my opinion, which I'll present in my perspective, of course. And then in the end, I'll talk a little bit about our own research, which is now funded by a couple of grants on the LA River, and how that information we're developing is, we think, going to be very helpful in, at least providing some basic data that will be useful in meeting some of the initiatives that are part of the second part of the talk. So that's kind of where we're going with the presentation today. So starting with part one, we'll mention the different water sources to Los Angeles, including imported water from 3 main sources. And we're going to go over this very quickly. We also have some local surface water supply really coming from, the events that are led by precipitation, particularly during wet years. And while the actual surface water is not directly used in water supply, it is used to do a lot of groundwater recharge when we have a lot of runoff. And so it's an important domestic source. And then we have these groundwater basins, which are used for storage of water from both category 1 and 2. And so they're highly engineered systems. I think the LA Basin is the most engineered system of groundwater basins and floodwater retention, control systems, and groundwater recharge basins and seawater injection barriers of any place in the world. A highly engineered basin. And it really is pertinent to some of these restoration issues that people want to do, but there are challenges to do that. In those groundwater basins, there's both natural recharge, coming from the streams, but recharge from input water from other sources like import water, and even highly treated recycled water and tertiary treated recycled water, wastewater, is used for recharge in these basins under certain criteria, certain retention times, certain levels of treatment, etc. And so these are, kind of the part one overview, and getting to the import water. If not for this import water from 3 distinct sources, probably Los Angeles would, without any kind of, some of the new novel techniques like massive desalinization of slightly saline water and even ocean desalinization, which is not highly implemented at the present. A little project in San Diego, but is a water supply if it comes to it. It's just very expensive. But if not for those potential, novel high technology applications, the internal water supply of Los Angeles probably would only be sufficient, and I should say the Los Angeles metropolitan area, probably be only sufficient for about 1.5 million people. And yet we have, in the LA Basin population of 18 or 19 million people. So, it's the import water which really led to the explosion of population and the growth in Southern California from these three sources. The first of which is the Los Angeles Aqueduct, which was constructed in 1913 with a second one completed. This is in Owens Valley. There have been movies made about this aqueduct because, there was a lot of contentious issues with the residents in Owens Valley because the water rights were acquired by buying up property, and then the water's been flowing to Los Angeles since 1913. A totally gravity-fed aqueduct. There are no lift stations in the Los Angeles Aqueduct. That aqueduct, which, was an important part of the Los Angeles water supply, very, very good quality water, was followed by the development of the Colorado River Aqueduct, which put claims on the Colorado River through the Metropolitan Water District in the early the 1930s. And so the Colorado River Aqueduct has been bringing water to Southern California since the 1940s. There's a lot of lift stations. It's a very engineered system, but it is a very, very important source of water to Los Angeles. A little bit saline. It's fresh water, but it has about 700 milligrams per liter TDS. The water purveyors in Los Angeles provide water at 500 and below milligrams per liter total dissolved solids. So they have to blend Colorado River water with other water sources or do some desalination to meet the local salinity standards for potable water. And then we had the really, really big system with State Water Project, which collects water from what's called the Bay Delta system. It gets runoff from the Sierras into the Sacramento and San Joaquin rivers. It collects. Used to have a very active ecological system here with the water running into the ocean, but as part of this system, water is brought through the Central Valley here for big, huge vegetable and orchard growth area in the United States. But it also brings water to many of the cities in Southern California as well. So we have these three sources of water supply that are imported. Those waters are definitely because of drought, because of interstate competition, because of ecological challenges where, various riparian systems are required to have minimal in-stream flows. Those sources are kind of fixed and even diminishing a little bit. So we have to, in Los Angeles, have some dynamic ways to continue to meet, some of our water demands. So we also have these internal rivers, which, as I say, the climate of Southern California is highly variable. There can be extremely wet years and then several years of very dry weather. But when there is wet weather, these rivers provide good source of water. And mostly not directly from the runoff, but through groundwater recharge basins where it's stored. There are some very large ones that have existed for decades, and now they're putting in more recharge basins and smaller systems that we'll also talk about. So this is part of the domestic water supply. It's important, and during wet years, we get replenishment of the groundwater aquifers, which at times are overpumped during the particularly dry years. Now, here are the groundwater basins, the notable groundwater basins in the Southern California area. Like, for example, we're going to be talking about our own research in the San Fernando Valley a little bit later, where the Los Angeles River begins. And this one, for example, is adjudicated, meaning there's a water master that is appointed to oversee the extraction and the recharge and the sustainable use of that basin. Several of these others are adjudicated. It is a court mandate where a water master basically has a team of engineers and scientists and policymakers who maintain conditions in the aquifer and then, issue acceptable amounts of extraction given the amount of water that's coming into them. So, A series of groundwater recharge systems exist throughout these. In many of them, there are seawater intrusion barriers in the West Coast Basin and in the main Orange County Basin. There's an extensive floodwater control system that really led to the Los Angeles River as it exists today, and other river channels that are concrete lined to run runoff waters quickly through urban areas and out into the ocean. Yeah, so these are, this is, highly engineered and managed set of basins. And these are also, as I say, used to recharge. They're recharged by imported water from those three sources. They're recharged by treated wastewater under certain regulatory framework, and they're recharged by the local runoff when the years are very, very wet. So it's a highly managed and developed system that's all part of our water supply. There was an act called the Sustainable Groundwater Management Act that was passed in the state. It was statewide, and this was, at one of the really high points of one of the droughts we've had recently. And with climate change, it's getting to be just a gradual change. It's not just drought and then wet years drought. There's a shift of more and more drying or less water availability. It's mainly related to temperature, I think, is what the literature says. And so we don't get as much recharge because of high evapotranspiration rates due to higher temperatures. But anyway, this particular act, which has designated a lot of money for the infrastructure to do some of these types of projects, like artificial recharge, and built into that are things like wetlands restoration and protection. It provides money to develop the infrastructure for more sustainable use of groundwater systems, particularly those which are not adjudicated with a court mandated water master. So that's an important aspect of continuing to have a sustainable water future in Southern California and elsewhere across the state. Now, this maybe ties a little bit more to some of the issues of the Los Angeles River and some of the other urban channels that we are investigating, and is the main theme of the talk. But TMDLs also ties into groundwater recharge, which really kind of goes back to these other two slides, because of the fact that we have these toxins that come from stormwater runoff, and two notable toxins are copper and zinc that are always exceeding the aquatic habitat standards when we have storm events. And they come from things like brake pads and galvanized surfaces like rain gutters and fences. Anyway, copper and zinc and some others are always exceeding the regulatory standards for TMDLs, total maximum daily loads, which is the maximum amount of a pollutant allowed to enter a water body under regulation to meet water quality standards. And so a TMDL kind of defines a management level that is allowable to be met. And if you're exceeding, then you're in violation of the TMDL regulations. So TMDLs are often developed on a mass loading basis. How many pounds of zinc or kilograms of zinc, how many kilograms of copper are flowing into these urban drainages. And one way you can control the mass loading to these streams is to capture the water, and whatever you do with it to capture it, and mostly that involves retention and recharge. So you're reducing the runoff into the urban streams, and therefore you have less flow, and so you have less mass loading of these pollutants. So there's a lot of effort to retrofit the urban basins with a lot of small scale types of recharge infrastructure. And unlike the very large water recharge basins, retention basins that cover dozens of acres, these particular structures are small scale swales and retention structures, gravel lined trenches, and dry wells. Dry wells are very popular now for trying to control runoff into our urban channels, and so that we can reduce the loading of copper and zinc and other parameters. And a dry well basically is a large excavated well above the water table that collects stormwater runoff and that then recharges groundwater, and then it reduces runoff into our urban streams. And that is a huge effort that is being implemented both for groundwater recharge, which is important, but and even more importantly for meeting these TMDL standards. And dry wells, here's some examples of dry wells being installed. There's a lot of these in some of your smaller commercial developments and businesses and industrial lots where we basically have installed these. But there's other efforts that kind of are complementary to that, like permeable pavement systems, which allow some of the water in what's considered impervious urban cover to allow some water to infiltrate. And that way it controls runoff. And then there's various retention types of infrastructure where the water is used for green belts and for wetlands and things of that nature. So there's a whole host of engineering efforts throughout the Los Angeles metropolitan area to put in these kinds of stormwater control systems and to help meet these TMDLs, which are so important from a regulatory point of view. And the purpose of these TMDLs is so we have less of this direct urban stormwater runoff into our rivers and streams. As you can see, it looks not particularly clean. That's turbidity, but no doubt that has a lot of copper and zinc. And then to put in, these dry wells and these bioretention planters and wetlands that allow stormwater to feed through the wetlands, and then with some of the intrinsic remediation, bioremediation that happens in the wetlands, then it feeds into the urban streams like LA River with a higher purity, and perhaps carbon, zinc, bacteria, nutrients, and other parameters like that going down significantly. So there's also a local bond which puts a special parcel tax of 2.5 cents per square foot of impermeable area. That this is just for Los Angeles and Ventura County, that is developing $280 million annually to put into these wetland restoration projects and dry wells and other ways that are directly mandated to try and reduce the TMDLs. And you see the way the money is being distributed from this pretty sizable amount of income from this bond. And it includes education and school training and the like, but the percentages, infrastructure development, administration, money directly to municipalities who make strides in funding their own project. And the one we like here is scientific studies. If it even gets 3, 4, 5%, that amount of 280 million is enough to support some pretty robust studies on the efficacy of these systems, and where we can put them in, and how, and what are their loading rates, and what kind of vegetation do we plant, and what is the maintenance issues. All of these things tie into scientific studies. So this is a pretty good program overall, and it's all tied together with the groundwater recharge and the TMDLs, and then some of the issues that we want to see that relate to equity, where our low income communities throughout LA is all concrete, no very little green space. And so putting these types of things in, it's sort of more an integrative approach to improving the quality of life throughout the city for all of our residents, rich and lower income. Okay, turning now to part 2. Excuse me, that should read part 2, not part 2. Sorry about that. But going to talk now about some of the LA River studies that we're doing, and some of the LA River water issues that really have provided the impetus for our studies, which I'll talk about at the end of the presentation. This is the Los Angeles River watershed. This is Long Beach here. This is the broader LA area. Over here is the San Fernando Valley, where the Los Angeles River has its origins, at the confluence of Bell Canyon Creek and Calabasas Creek. The LA River then flows east through the San Fernando Valley. It then kind of turns to the south and then moves down and issues into the ocean in Long Beach. About 54 miles of, and what would that be? 80 kilometers of stream length. And most of it is concrete lined, as you see here, but there are 3 sections that are not lined with concrete. The first is at the Sepulveda Basin, which is an area where there's a dam that is used for flood control, but it rarely floods Sepulveda Basin, so it has, all kinds of recreation and parks for the residents to use. But that reach is unlined. Then there is an unlined section at the bend here. We call this the Glendale Narrows, where the LA River turns to the south. And the reason is there's so much rising groundwater here that it was impossible to put in a concrete lining because too much groundwater issuing, and so they left that part unlined. And then the river flows through lined reaches of stream until it reaches the lower part where it issues into the Pacific Ocean. And because of tidal fluctuations and some habitat issue, the LA River is unlined here too. So most of it is lined, as you can see, but there's some important areas that are not, that are part of our investigations. Purpose and reasons for doing the study. There's going to be really significant changes in LA river flows and river water chemistry for some reasons I'm going to point out in just a minute. But if you're hearing me talk about water being retained from urban runoff and used for groundwater recharge, well, what's that going to do? It's going to diminish runoff into the LA River, and it's going to create more groundwater recharge, which is going to raise the water table and create more groundwater seepage. So those are that's an example, but there are going to be many, many changes. Some of these changes may weaken or improve ecosystem health. LA River is not part of water supply per se in Los Angeles, at least at this time. It's really all related, the LA River, to recreation and ecological habitat, and to the water that runs off into the Pacific Ocean, where there's also ecological habitat, but recreation. So, some of the toxins in LA River discharge, you can sicken people and some of the marine species that live there. So that's the main reason for doing all this LA River stuff. And our studies will look at changes in river flows, watershed chemistry. Or some of our biologists are looking at ecosystem behavior and response. And it provides really a wonderful opportunity for doing research and integrative research. And it's really getting underway, at least for our lab. And what I'm going to talk about here for most of my presentation today relates to dry weather flows, which means, as I say, we do have these couple of months of wet weather in Los Angeles, usually. But at least 10 months of the year is almost all dry weather conditions, and that's an important part of our investigation, which I'm going to focus on today. Now, so I've already mentioned how the LA River turns to the south and issues in the Pacific Ocean. I did want to show, though, that this is the Sepulveda Basin. It's that first part that is unlined, and it's, as you can see, there's lakes and trails, and then there's a dam over here too. This is the unlined section here at the Glendale Narrows, where, as I say, rising groundwater made it impossible to line the bottom, so groundwater seeps into it. Down here is the unlined section closer to Long Beach. Well, the reason I'm putting this slide in is because there are 3 wastewater treatment plants that issue tertiary treated wastewater into the Los Angeles River. Tillman is the largest of the 3. And LA River, almost all of its flow is coming from these wastewater treatment plants. And so, yeah, I mean, these people like wastewater. Well, that's that's the flow of the LA River. It is highly treated, tertiary treated, but yeah, that's the flow of the LA River, except above Tillman. And so it's a very important point because there's going to be different uses of this wastewater besides just discharging it into the ocean. That's going to lead to the changes of flows and chemistry during dry weather conditions. So I wanted to definitely put that slide in there. So dry weather conditions, aside from the wastewater discharges during dry weather conditions, what are the sources of flows into the LA River? Well, one is going to be just your dry weather urban runoff that gets into the storm gutters. And, they're trying to reduce this because it's wasting water, but inevitably it happens. People wash cars, people water, the sprinklers break. And so dry weather urban runoff is an important source to the LA River, though not nearly as significant as wastewater discharge. But also something that's not thought about as much is groundwater seepage, and not only in unlined sections, but along line sections. And we see and can account for, significant loading of nutrients like nitrate, and some trace elements like selenium from groundwater seepage. And here's like a underground storm drain. This is all groundwater seepage creating all of this flow. This is groundwater seepage along a joint squirting out of the underground drain. Same here with a manganese stain and an iron stain. Tells us a little bit about the chemistry of the water. And this just shows how when you have water table above storm drain grade, these things leak. And so groundwater flow, even in the line sections of the river, are important. We've shown that, and then I'll show that today. Now, I'm going to take a pretty simple diagram I drew up. And remember, I said the LA River makes this turn to the south. So this diagram is sort of a primitive representation of the LA River from its headwaters to the ocean. And the width of these lines represent the flows, and semi-quantitative. This is based on my own knowledge of the numbers. But it starts off with, your dry weather urban runoff and then some groundwater seepage until these wastewater discharge plants are reached. And then the flows go way, way, way up. There's some rising groundwater at the Glendale Narrows here. And then there's other dry weather urban runoff, and then the water issues into the ocean. So that's kind of the present conditions, present LA River. But what's going to happen is there's going to be some big changes that are going to take place and that are starting to take place. And they go back to these TMDLs and groundwater recharge and some of these other issues. And we already know that this treated wastewater, which is discharged in the ocean, is going to be used much, 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 much more for our domestic irrigation water supply. So, we have what we call purple pipe all over Los Angeles, and the cities are putting more and more of this in, where the recycled water is used to irrigate our golf courses and road islands and parks, not individual residential properties, but all of the different areas where we have vegetation. And this is proliferating widely. And so what's it's going to do is it's going to reduce treated wastewater discharge into the river, and then use a lot more of this for water supply. And also it's being used more and more for groundwater recharge to ultra pure levels of treatment. So with these changes, then the wastewater flows are going to decrease. And so we'll get something like this. Wastewater discharge is going down. What's going to happen though? Some of this water will become groundwater recharge. So we'll get more groundwater seepage. So that will go up. But overall, because of evapotranspiration losses, most of this landscape irrigation will evaporate away. But there's other real pertinent factors that are happening. There are tax incentives we're semi-arid region. LA, some parts of it, Beverly Hills, and just, a couple of decades ago, everything was green, everything was watered, everyone had a green grass. Well, now there's a lot more initiative for convert residential and commercial areas to drought tolerant landscapes. And the one way that's the price of water has gone way up for citizens who want to save money on their water bill. we're going to see less import water from those three sources because, as I say, it's interstate competition, ecological competition, drought and climate change. Those are going to create some changes, and all of this is going to reduce the urban runoff, dry weather runoff. And then we have a lot of really old infrastructure with leaky sewer lines and leaky water pipes. The leaky water pipes in particular, old clay water pipes. I'm sure you have a lot of this in Chihuahua and Juarez, where there's so much leakage from these, and it recharges groundwater, and then it's a loss. And particularly a concern when it's water pipes, because that's water supply. So yeah, there's a big initiative to find these leaks, repair them. So that's going to decrease groundwater recharge, which in some places, as much as 10% of the water supply is, and including in Los Angeles, is lost through pipe leakage. So these are all going to change the conditions of the LA River, and that's one of the reasons we are studying it now. We need to establish baseline data that is going to allow us to look at changes, sort of like a long-term ecological research study. And that's what's driving at least a part of our project today. Some of the anticipated changes, just coming from what I just said, is diminished river flow and diminished dry weather water output to the ocean. So, that's just going to happen. And those bays and estuaries that receive LA River discharge during dry weather, they'll have to, they'll adapt. They'll adjust to the changing outflows. And some level, the quantities of LA River flow are going to change, not only the flows, but the chemistry from all of those factors. And so that's going to affect the pollutants. Don't know. In some cases, it improves the water quality. In some cases, it might create conditions that are not as good as they were, than even treated wastewater. So these changes are going to be happening, and it's driving a lot of our research. So we're investigating discharge conditions, changes in water chemistry. We use a lot of isotopes in evaluating the LA River, and then we have some other people working with us that are doing things as part of our studies, looking at some of the more wet weather conditions, rainfall runoff analysis and modeling, and that has changed with much more higher intensity rain of shorter duration and less frequently than had been the case before due to climate change, is what they tell me is happening. And then we have some people looking at the fire ecohydrology, and that can relate to how runoff conditions and hydrochemistry changes. Just want to make the point that because of equity issues, we're putting in a lot more urban agriculture and urban gardens. They require green areas for pollinators because urban agriculture and urban food gardens need to have pollinators. So there's this huge effort in Los Angeles to do these urban retrofits. The equity issues for lower income communities really want to get more parks and green belts and recreational areas. And what I'm going to turn to next is the stream restoration issues, which is kind of what we're interested in. So stream restoration, everyone wonders why the LA River is concrete lined. You got to put yourself in the mindset of the citizens of the time. When there was a huge flood in 1938, killed 138 people. They had little towns spread around the Los Angeles metropolitan area. They had nature everywhere. Here, for example, this is Griffith Park over here, a highly urbanized part of the LA River. This is the LA River before being lined, maybe in 1905 or so, a little weir here. Very low flows during dry conditions, but there was nature everywhere. The urban areas needed to be tamed. We needed, not to lose 130 citizens through flooding and through debris flows. So this led to, the lining of the LA River starting in the late 1930s and 1940s to basically control floodwaters. And so that's how the LA River became lined, and the conditions that continue to this day. Public image, this is what the people think of the LA River, very sterile environments, not particularly fun to visit, no real ecosystem to speak of. But there's a lot of people who want to remove this and they want to replace it with, natural stream. And there's some engineering and economic challenges to that. One of the arguments for getting rid of this is how much more it will improve water quality, where we know that unlined channels have riparian areas that can improve water quality through the vegetative uptake of toxins, bacteria, trace elements, even organic contaminants, nitrate reduction due to uptake by vegetation, reducing the conditions into nitrification. All of these, and we know that online channels will provide those benefits to stream water quality, whereas line channels, you don't have those kind of riparian systems with a lot of carbon and a lot of organic matter and hyporheic zones like this that have fungi and bacteria that create a lot of transformations that achieve these. So that's one of the reasons on kind of a water quality point of view. Also, these kinds of systems, again, they have recreational benefits. They have pollinators that are needed for our urban agriculture that's going into the city. It's much more pleasant aesthetically, improves the quality of life, and makes people have just, and it also relates to things like urban heat island, which we have a big problem with in Los Angeles. It lowers the temperature due to the urban heat island. And it has little micro level improvements on the CO2 footprint. So all of these are real positive things to be done, but there are challenges and impediments to removal of concrete lining that we're gonna look at now, because some people, it's sort of a romantic vision of the whole LA River being restored, but we have to look at some of the technical issues and challenges that are impediments to removing all of that concrete lining. And I'll just take a very simple example of stream discharge, how it's measured on a very simple geometrical channel shape. It's just simply the stream flow or the discharge, which is used for, setting flood control, maximum flow type design standards, etc. It's just simply the stream flows, the width of the channel times the depth of the flow times the velocity. And that gives us cubic feet per second or cubic meters per second. And, of course, we don't just have that kind of channel. We can measure in an unlined channel the discharge through little incremental sections and then adding them up. This can be done with a boat. It can be done by weighting. It can be done on a bridge that's set up for stream discharge measurements. We measure the width, depth, and velocity in each increment and then sum them up. And then there are rating curves too, which are set up in urban channels, which give us discharge based on the stream head. So, we can do this. But one problem, if we remove the concrete lining, the velocity slows down. And so if the discharge is a function of velocity, what that means is that we have to have a larger cross-sectional area to carry the same amount of flood water away because the velocity is slowing down. And so that's certainly an impediment to doing a retrofit and removing the river lining. Because why? Because so much of the city and commercial areas and residential areas are built right up to the sides of the LA River. And so it's a huge challenge to think that, you can remove all of the lining of the channel because it was designed for certain floodwater conditions, some sort of 100-year flood event type design. And if you slow down the velocity through removing the lining, you have to increase the cross-sectional area, and that can only be achieved by expanding the channel. And there's erosion issues too, so there's a lot of capital that's needed to do that. That is economically definitely, I think, would be challenging. So there are other ways that we can have restoration efforts. And my friend Mike Beelan sent me a document the other day where this very issue is being done in the LA River. This is in Arroyo Seco, which is, one of the old concrete line channels that is a major tributary to the LA River, but it has this concrete line channel. But it also has a channel grade where water is collected from during the dry weather conditions, and it is fed through a diversion structure where a riparian area is planted. And so the flow of the LA River moves through this off-channel online section of channel that was created that has it has all of those things. Water quality improvement. It has, you can see the trees here, the water flows through, it sustains the trees. It has a wildlife corridor and pollinator benefits, and then it flows back into the LA River, into the Arroyo Seco on both sides. And so there are a lot of people hike around here. There's trails, and that's an alternative that is certainly manageable if you can just, kind of grab pieces of property and parcels and then develop these offline systems that retains the central drainage channel. That's a pretty effective approach. And so we're going to see a lot of this, I think, where we see some of our railway lines and industries. There's a lot of money that people want to commit to putting these types of systems in. But the whole LA River, yeah, that's gonna be a very, very huge challenge, because it's just, trillions of dollars worth of homes and infrastructure. There's also different sections that can be restored in different places if the land is available. For example, this is in a different area, but a study that we did. Here's a couple of our students. This is groundwater flowing out of a weep hole here, out of a concrete line channel. But this was managed by the Los Angeles Senate Flood Control District, and the city came in with the Los Virgenes Municipal Water District, and they wanted to just replace this little section of unlined channel with a riparian corridor. And just this little section is about 200 meters long. To remove it and replace it with this unlined section, it was about $3 million without paying for the cost of the property, just the replacement. And you know what else? The flood control district says, okay, you can do this, but now you take responsibility if there's any flooding, and then you maintain it. And so now the city of Agora Hills and the Los Virgenes Municipal Water District foot the bill for this real nice little online reach of channel, but they assume the liability if something goes wrong, and they have to pay for the maintenance. So those are some economic challenges, but I think anyone would agree this was pretty cool. How are we on time? Because I know we started a few minutes late, but I probably need 6 or 7 minutes to finish up.
We still have time, Professor, about
Okay, but this will go pretty quickly because I just want to touch upon what our own study is doing. Here's a couple of students who started in 2002. This is Ariel Camareno. She just defended her master's thesis. These were a couple of summer students who are doing real well, but just want to touch upon our own research, which is supported by various grants, the biggest of which is a Department of Energy grant, which is really covering, all of our studies of the LA River now. But we have these training grants from Department of Agriculture and NSF, where some of our undergraduate students come and participate in these efforts. And there's some money that goes along with each student, so it helps augment our research budget. And we've had a pretty long history of working in the urban environment. These are a couple of journals where I was either the co-guest editor or the guest editor that covered urban groundwater or urban hydrology. And these are two of our students, by the way, and this is one of our students along a channel that's been eroded. So yeah, we've been pretty active in this in Los Angeles all the time I've been here. But now getting to our study, we have several studies along the LA River that are recently underway or just getting started. So this is our 2022 study, which I'm going to talk about, but we have a student who's going to expand that and look at the data from 2022, because we've had very wet weather. We want to compare the peak of the drought to the really wet weather, but also expand to reaches we didn't look at. Along the online reach, we have a student who's been looking at this reach since September. A new student is going to be studying Reach 3 from downtown LA to Long Beach. And then we have a couple of students looking at tributaries. And then my other colleagues are looking at burn hydrology, as I say. So they can talk about that themselves another time. But these are all studies are going to, and I'm going to just show you real quick the results of the 2022 study. And I'm probably going to take about 6-7 minutes. Is that okay? Is that
Yes,
going to be?
please go ahead.
Oh, okay. So I'll try to wrap this up as quick as I can. But the 22 study covered this area here above the Sepulveda, well, down to the Sepulveda Basin and where the wastewater discharges just start. So all dry weather flow during the summer. And interestingly, we're going to see there's a lot of groundwater coming into the system, even though it's totally lined until we get to Sepulveda Basin. What motivated the study is historically that reach had been unstudied. It was the first major study that I've been able to see where we integrated trace elements and nutrients and isotopes. Again, trying to form this baseline data in case there is some level of restoration. And then, to support, any kinds of discussions about stream restoration along that reach. Real quickly, the parameters measured are a variety of major ions, nutrients. Selenium's an important one that we've had a real interest in. It occurs naturally from geological sources. I'm not going to talk about the isotopes, but they are part of our evaluation as well. I want to show that this is the study reach from this area here, and it's fed by very, very different types of, or it's flanked by very, very different types of rocks. The green are marine rocks that are of very fine texture that contain a lot of selenium, uranium, nickel, very high content that leaches from these. Then over here, there's some marine sandstones and conglomerates, not nearly as soluble or with the trace element content of these marine siltstones and shales. And then over here are these granitic rocks, which are igneous rocks, and dioritic rocks, which are very low solubility. And so it's interesting that it became evident to the early investigators that on the two sides of the basin that reflect the geology, on the west side and on the east side, the water quality is extremely different. And even in 1933, they noted that the water on the northeast side of the valley is very different in terms of sulfate content, and as we found out, trace elements as well. They could define a line of demarcation at Pacoima Wash. And this is Pacoima Wash. And we're going to show well data on the west side and on the east side of Pacoima Wash from 1933. Notice here from 1933, here's the sulfate content in milligrams per liter on the west side of the wash and on the east side. That's huge. It's more than an order of magnitude. And it all relates to the geology. And so Settmeyer, looking in 1985, kind of with more data, noted that the majority of streams in the western part are these very soluble sedimentary rocks. They contain a lot of gypsum, and so they have a lot higher dissolved solids that run off and that dissolve in the groundwater. Whereas in the eastern part of this basin here, where we have all our water wells, these are sands and gravels eroded from these sediments, from these rocks, that are very, very sweet waters, very high purity waters. And so they note that in the east side that the groundwaters are very, very good quality. So we have very, very different kinds of chemistry of the water. The strata that is formed from eroding granite, if you put precipitation recharge to it, it ends up being low TDS, very good potable water. Whereas the strata that is eroded from the marine rocks, if you put precipitation to it or any sort of water, its TDS goes up due to dissolution of sulfate. And there's also those trace elements as well. So looking at Settmeyer's map, you can see in TDS ranges here, Reds, this is for groundwater, and you see these are the very high salinity, and this is the LA River here, by the way. Green is coming off these sandstones, which is sort of mixed, so it's a little in between, but not as saline as these areas with red shading, which are greater than 850 milligrams per liter TDS. And then over here where we have all of our wells, less than 350 mil, this is where all the wells are put in. And it's all related to the geology, all because the strata comes from erosion of these granites. And so the water in contact with it has very low dissolved solids, and that's where the wells are put in. So for example, our study area over here, here is a well hydrograph. There's no pumping over here, maybe for a couple small industries. This is a well hydrograph seeing no changes. Whereas over here, where we have this very, very good quality water and big Department of Water and Power water wells, this is showing fluctuation of groundwater levels due to pumping. And so that's very important because this whole area is very saline and this area is very dilute. And so our study, which focuses here, is mainly in this area that is going to be in the more saline strata. And so this is the study area. This is Sepulveda Basin. Here's the confluence of two creeks. And we found in doing our investigation that this upper reach has groundwater discharge through weep holes and groundwater seepages, but the water table is below channel grade over here, and then the wastewater discharges come in at Sepulveda Basin. So we got gaining stream conditions here, and these are all groundwater seepage points, and then we got losing stream conditions over here, even though it's a concrete line channel. So, and I'm just going to go, because I know I'm out of time, I'm going to go quickly through the data, but the LA River is shown in blue stations in our study area. Tributaries that come in are shown as orange. And then groundwater seepage, these are all groundwater seeps, which I say end at this line. These are groundwater seeps through a concrete line channel. So let's look at this. So this is data. This is the river salinity in total dissolved solids. Starts out very high because the tributaries that create the flows at the headwaters is very high. This is pretty high quality or pretty poor quality water. But notice the TDS drops, and that's because the groundwater coming in is lower than the tributaries. So that drops the TDS. Then groundwater seepage stops and the salinity stays the same until we reach the point where the wastewater inflows come in. And our treated wastewater is much more dilute than the natural flows of the LA River above the wastewater input. So we get this change in the salinity of the LA River. That's pretty dramatic. And the same, this is sulfate here. Sulfate drops because groundwater has lower sulfate, still high sulfate. Then it's stable. Then the wastewater outlet has lower sulfate, so the salinity of the river drops. Nitrate's a different story. Here is the LA River at the confluence, and then it goes up. Why? Because the groundwater has much higher nitrate nitrogen concentration. So groundwater is flowing in and increasing the nitrate. Then not much change along the part of the channel that has no groundwater seepage. But then the wastewater input, which has a bit more nitrate, increases the nitrate at Sepulveda Dam. So it's about half, a little bit less than half the drinking water standard of 10 milligrams. We can see the importance of the groundwater flows and the wastewater flows on all of these constituents. And the final one is selenium, which we didn't have a budget to study all of it. So we did all of just the samples along the reach that is fed by groundwater. This is the aquatic standard for selenium, a US standard. Selenium goes up above the standard, and that's due to all this groundwater seepage, which is above the standard. And that's where our data ends. But we can see that because of groundwater seepage, our selenium goes up along that reach, and it's above the aquatic standard for protection of migratory waterfowl. I'm going to end here and just mention, because I know I'm out of time, my apologies for being a minute or two over. But our future plans, we're going to continue to do similar work along those 4 designated channel segments that I just showed you for 2022, which was done very quickly. a lot more technical aspects to that, but I've just wanted to throw, what we're doing there. But we're also going to do this big synoptic study where we're going to, on over a period of 2 days, sample the main stations on the main channel at many stations, and then all the tributaries, and we're going to throw everything at it: isotopes, trace elements, nutrients, major anions and cations. And we're going to be a very detailed study, and we're going to do that in July and January over like about 2 days. I'll have about 10, 12 people at least out there. I want to go ahead and wrap up. Just real quickly, we can see, from everything I've said, there are going to be dramatic changes in the infrastructure, in the management of the basins, in the flows of the LA River and other urban streams due to all of these changes and retrofits to the urban environment. And so there's a lot of management decisions going into how that's going to be accomplished. And our part is to gather the technical data to see how these changes relate to things like the ecosystem health and quality of various standards of water quality. And hopefully you can see that our work is serving a very beneficial purpose in the work we're doing. So indirectly we create curriculum that ties to all of these issues and stewardship of the water supply and water resources. We're trying to create a well-trained workforce who are informed and knowledgeable about these issues and have the skill set and technology and ability to kind of provide the management personnel needed to make the best decisions. And then, like I say, we're doing these studies ourselves, and we hope that they're going to be useful and of value to the regulators and policymakers to help them make the robust decisions that are needed for all of these changes that are underway and that will continue for some years to come. And that'll do. I'm happy to take any questions. And thank you for your patience. I know I went over a little bit, but
it doesn't matter. We have some questions over here.
Could I just say one thing? If there's anyone that has to leave, please, you got to get to your next appointment, whatever. Absolutely, please do. But yeah, what questions? Happy to.
Well, first of all, it says Michael Bieland. Great
Yeah.
talk, Mari. Sorry, I got to run.
Okay.
Also,
It's
we
all
have
right,
some.
Mike.
Also, we have some questions in the Facebook Live transmission. How do you imagine Los Angeles water supply will be like in 50 years?
Boy, that's that's an interesting question. I can't say I've really pondered it myself for any period of time. Maybe I should, but it depends on the climate trajectory. It depends on economic growth and additional development. Obviously what we have, the ace in our hole is we have an ocean right next to us. And, there are countries in the Middle East, Saudi Arabia, which a big part of their potable water is met by ocean desalination. It's very, very expensive. But it is water that if you need it, and if the regulatory hurdles to using it are sort of scaled down, because right now it's very, very tough. That is water supply, but very, very expensive. Probably more likely there's a massive amounts of slightly saline water where desalination, if we really find that there are water availability problems, that we can do desalination of a lot of slightly saline water at much more economic levels. But we have this imported water, which is always going to be meeting a significant part of our demand. There's a lot more improvement in the infrastructure and conservation, and all the things that I've talked about. Obviously, steps are being taken to meet our future water demand. The price it's variable, it's pretty high, but you know, it just will be passed on to the consumer. And so, you know, people will adapt and they will do their own types of residential conservation. Um, Whether or not the farming takes a big amount of our of our water in California, and you know, there's cities that will pay for that water. So whether there'll be transfers, short-term transfers, or permanent transfers of water to the municipalities from the agriculture, you know, not sure, but yeah, I feel pretty good about the future overall.
Great. Uh, just give me a second, please. The concrete removal in Los Angeles is similar to the Kissimmee River Restoration Project in Florida.
Okay, could you repeat that?
The concrete removal in Los Angeles River is similar to the Kissimmee River Restoration Project in Florida.
Are they asking if it is?
Exactly.
Well, so keep in mind that the removal of concrete over the LA River is only, it hasn't really developed to any appreciable level in the LA River itself. It's a lot of conversation, a lot of plans. You know, there's a lot of some of these different types of diversion systems that are going in where the concrete channel remains, but the water is being diverted into areas where they previously had railway lines and industries, that those were acquired, those properties, and now they're putting, you know, like greenways and wetlands that people can hike around, and then the water is diverted back into the LA River. So there isn't really in the actual channel of the LA River any direct concrete lining. To the example in Florida, I'm not really familiar with it, so I don't know where they are as far as progress, whether it's moved forward. So I can't really comment on that.
Okay, well, we are going to ask this last question because we don't have we're out of time.
Oh yeah, no, I'm sorry to go over a little bit too long, but please, yeah, I'm happy to take any questions for anyone who.
Um, this is the last one. Do you know about the toilet to tap policy?
Yeah, well, of course, I'm familiar with the conversations about it. There are advocates for it who claim that yeah, that the technology is sufficient, and you know there should be no uh, public concern about doing that. It's been talked about even since I was a PhD student, and that was a long time ago, and that was in Texas, by the way. The public perception of that particular process, I think there just will always be just kind of a resistance or disgust even thinking about it. But I do think that there can be, and my even my neighbor, I have a little tiny cabin in Arizona. He has a septic system, but he has a little treatment system where that water is safe to be used on his garden, on his property, but not for drinking. I personally would not feel all that inclined to drink from toilet to tap. But you know, the people and engineers primarily who believe in that, you know, feel that it's totally acceptable. You know, little small residential systems. I can tell you the highly treated wastewater that is used to recharge Orange County Basin and now in the Los Angeles San Fernando Valley goes through such extensive purity, even more than the El Paso treatment system that's kind of was a standard for high purity water treatment for groundwater recharge. They will give you on a tour the water that is going through their treatment process, and they'll ask you to drink it, you know. So, but myself, I probably would not want to do that. There's, you know, emerging contaminants of concern, hormones from our drugs and things of that nature that are not sufficiently tested, in my opinion. I'd much maybe more comfortable with it going into the ground and residing for 6 months, and then mixes with native groundwater and other sources, and then is drained, is consumed. Yeah, but the public is always going to be resistance in LA, I think.
Okay, well, with this, we will finish this webinar. Professor Hibbs, thanks again. This has been very, very interesting. I will send you your recognition certificate by email. And with this, we conclude this webinar. We thank everyone for attending, and well, see you next time.
Thank you, and thanks for the invitation. And you know, it's been my pleasure, and I hope I'll meet you sometime, Dr. Nunez. Maybe when I'm out in El Paso or something.
For sure.
Okay. Okay,
Well,
but
thank you.
thanks everybody. Enjoy your day.
Thanks.